Look around you and you will see millions of colors. All of these colors actually come from pure white light. A long time ago, back in the year 1666, Sir Isaac Newton discovered this phenomenon by passing a beam of light through a prism. Through this discovery, we are now better able to understand the building blocks of color more specifically. Color theory is quite expansive, but on the simplest level, it helps us create a logical structure for color based on the color wheel, color harmony, and the power behind how colors are used together. On a basic level, colors can be broken down into similar color families, such as reds, yellows, blues, greens, and so on. This is where artists and designers begin to use derivatives of these colors to create designs with purpose and poignancy. But in the end, color comes down to how the eye perceives it. Who remembers the great debate over what color the dress was? According to the New York Post, neuroscientist Pascal Wallish concluded that the differences in perception came down to our assumptions about how the dress was illuminated. This concept is further explained in the following slides.
We interrupt our program to bring you this important message.
Before we get too far, we should talk about how we see color and why that matters. The human eye's photoreceptors are made of rod cells and cone cells that are sensitive to light in different ways. Rod cells are sensitive to the intensity or brightness of light, but not at all to color. Cone cells are sensitive to the specific wavelengths of light, but to a vastly lesser degree, the intensity of light. Humans are trichromats, meaning they have 3 different types of cone cells: red, green, and blue sensitive cone cells. Nearest the center of the eye is an area that is incredibly densely packed with cone cells. This means that your color vision, as well as your fine detail vision, is at its peak in the center of your field of vision. Outside of that area is where rod cells become more numerous, beneficial for low light vision and increased awareness of motion in your peripherals. Of the 3 types of cone cells, the red are the most abundant at 64% of the cone cells, then green at 32%, and lastly blue at 4%. As light is focused onto your retina by the lens at the front of your eye, and maybe your glasses if you have them, the rod and cone cells are stimulated into sending electrical impulses through the optical nerve to the occipital lobe of your brain, which then interprets these signals and creates the images we see. So, with the knowledge that our eyes are reactive to red, blue, and green light, it makes sense that the primary colors of light in the additive color system are red, green, and blue. As you can see here, combining red and blue creates magenta. Red and green makes yellow, and green and blue make cyan, with white being all the primaries mixed together in equal proportions. The same concept works in your eyes. As different ratios of red, green, and blue light are absorbed by the cone cells, they'll be combined and interpreted as secondary and tertiary colors. Now, I bet you're going, Mr. Petros, this is way too much science for me right now. Heck, this is theater. It's art. Why do I need all the science? And I understand, but you're forgetting one thing.
Science rules.
Theater is the perfect blend of art and science. It can't be escaped, so embrace it. Embrace it and take advantage of the science. How do we take advantage of the science is absolutely your next question, to which the answer is, in any way you can think of. A few examples include using primary blue top lighting as a scenic transition light cue because it makes it hard for the audience to see. Since people comparatively have so few blue cone cells, our eyes focus so much worse in blue lighting than in red or green lighting, so us lighting scene changes in blue helps hide things. Also, we can use how objects reflect light scientifically to our advantage. What I mean by that is that when light hits an object, one or more of 3 things happen. It's absorbed as heat energy, it's reflected, or is refracted, or bent as it passes through the object. Now for a controversial statement. Objects do not inherently have color. They have the potential for color. Their color is granted to them by the lighting they're in. Look at these Rubik's Cubes, for example. can you tell what color the squares are beyond red and more red, blue and more blue? In the white light, we see the rest of the colors because the white light contains all the wavelengths of light, allowing each square sticker to reflect the full color it's able to. This chart is a handy way to look at how objects will look under pure, specific colors of light. Please note that this chart makes a ton of assumptions and will fall apart when faced with the reality of impure ink or dye in the objects and imperfect light sources. But we can see that a red object under red light will generally appear red, but under blue light it will have no color or look black. This is true for objects that are primary colors under primary colors of lighting. Similarly, a red object will only appear red if it's in a secondary color of lighting that also contains red, such as magenta. And vice versa, a cyan object will appear to be one of its component primary colors while in that color of lighting, and will only appear to be that cyan color while in cyan light.
Now back to your regularly scheduled program.
Returning to the concept of color theory and Newton's prism discovery, we can break colors down by using a color wheel. In this example, and moving counterclockwise, we can observe the prism on the spectrum of red, orange, yellow, green, blue, indigo, and violet, or Roy G. Biv. When it comes down to color mixing with pigments, we have to go back to our earliest introduction to primary colors. Ratios are very important when mixing colors. Only a true 1-to-1 ratio will give you a pure secondary color. In percentages, we would consider this 50-50. So a 1-to-1 ratio of red and blue will give you a true violet or purple, just like equal portions of blue and yellow will give you a true green, and the same concept when mixing yellow and red will give you a true orange. The next level of color on the color wheel is known as a tertiary color or third color. A tertiary is achieved by mixing more of a primary color into a secondary color. In this example, we see a true violet being mixed together with a higher ratio of red to achieve a red violet, a pure green being mixed with a higher ratio of blue to achieve a blue green, and a pure orange being mixed with a higher ratio of yellow to achieve a yellow orange. When identifying the tertiary color name, the common practice is to apply the color of the primary in the higher ratio to the name of the secondary color. Some examples not shown here are blue-violet, yellow-green, and red-orange. Now that we understand how to mix colors together when it comes to pigments, we will look at how colors work together in color schemes. The first color scheme is known as complementary. As shown in this example, complementary colors are the ones that are located directly across from another color on the color wheel, like yellow and purple. They complement each other because they are each other's strongest contrast in the color wheel. Therefore, they help make each other stand out. Let's look at this concept in terms of popular business logos. In this example, Krispy Kreme has taken advantage of the strength of red and green. In the following examples, 7-Up utilizes the same complementary color scheme as Krispy Kreme, and Hallmark makes their logo stand out with purple and yellow. Can you guys think of any other business or sports teams with a complementary logo? The next concept we'll cover in color harmony is the split complementary color scheme. The split complementary color scheme is a variation of the complementary color scheme. In addition to the base color, it uses the two colors adjacent to or next to its complement. So in this example, we have a yellow base with a red-violet and a blue-violet split complement. And in the following example, we have a base color of red being used with yellow-green and blue-green. Split complementary colors are great for having contrast and showing emphasis without being as jarring as complementary color schemes. In this example of logos, we can see how Fanta uses an orange, blue, and green split complement, while Tide uses blue, yellow, and orange. Can you guys think of any other logos that use a split complementary color scheme? The next color scheme we will look at is known as analogous. Analogous color schemes use colors that are next to each other on the color wheel. They usually match well and create serene and comfortable designs. Choose one color to dominate, a second to support, and the third color to use as an accent. In this example, the yellow is dominant, while you might use yellow-green as the supporting color and yellow-orange as an accent. In this logo example, BP uses green as the dominant color, with yellow-green as the supporting color, and yellow as the accent. This next example is a little more difficult to prioritize colors, but as you can see, MasterCard uses the analogous color scheme in a simpler way, using red, orange, and red-orange where the circles overlap, much like a Venn diagram. This next color scheme we will look at is known as triadic. A triadic color scheme uses colors that are evenly spaced around the color wheel. Triadic color harmonies tend to be quite vibrant, even if you use pale or unsaturated versions of your hues. To use a triadic harmony successfully, the colors should carefully be balanced. Let one color dominate and use the other two for accents. In these examples, two popular brands, Firefox and Burger King, use the same color combination in a very balanced manner. Can you identify other brands that use a triadic color scheme? There are many other ways to combine colors in a purposeful manner. So far, we have addressed hues, or colors by name. But there are other variations of hues known as tints and shades, and have to do with the perceived value of a hue. Value refers to lightness or darkness of a color. It indicates the quantity of light being reflected. When referring to pigments, dark values with black added are called shades of the given hue name. Light values with white pigment added are called tints of the hue name. The final colors seen here are known as tones, which is achieved by adding shades of gray. The concept of value can possibly be best understood by looking at the gray scale shown here. When applied to color, we would start with the pure primary or secondary color at the center of the scale and progressively add higher and higher ratios of black or white to achieve the desired shade or tint. This concept can be applied to shade and highlight scenic pieces to make them stand out on stage. And it can also be applied to creating a monochromatic design. Another way to affect the value of a color is to progressively add two complementary colors together in larger and larger ratios. With this approach, you will almost always achieve a neutral brownish color as each color cancels the other out. Sometimes this is a better alternative to adding black to a color to achieve a good, believable shadow color. Looking at this example, you should notice this can be accomplished by any complementary colors on the color wheel. This concept should help you begin to understand subtractive color mixing, which is the type of color mixing we are talking about when we use pigments or paints. Subtractive color mixing is creating a new color by the removal of wavelengths from a light with a broad spectrum of wavelengths. Subtractive color mixing occurs when we mix paints, dyes, or pigments. When we mix paints, both paints still absorb all of the wavelengths they did previously, so what we are left with is only the wavelengths that both paints reflect. It is called subtractive color mixing because when the paints mix, wavelengths are deleted from what we see because each paint will absorb some wavelengths that the other paint reflects, thus leaving us with a lesser number of wavelengths remaining afterward. In the most practical sense, this means that when we mix the pigments of yellow, red, and blue, and we bring them all together, we should come up with what is nearly pure black.